Okay, so we're going to talk about continuity. And the first thing that I want to discuss is an informal definition, one that you would have learned in, I guess, college algebra. So in college algebra, for example, we might give you a graph, and you would characterize it, if it was continuous or not, by determining whether or not you had to pick up your pencil when you drew that graph. So if I'm looking at this quadratic, it looks like that I've drawn, I can draw that without picking up my pencil, and I can easily say from that definition, this very informally, that this is a continuous function. However, if I start looking at maybe, we'll do like a piecewise defined function. I had to pick up my pencil to draw that, and so I can say that this is not a continuous function. And I can start discussing where the discontinuities exist. So for this class, since we're in calculus, that definition's not good enough. And so we're going to talk about what it means formally to be continuous. So let's talk about continuity at x equals c. And so we're just going to use c as our indicator here for talking about continuity. And we're going to say that a function is continuous at x equals c if the following three conditions are satisfied. If you are one who likes making like flashcards, this is a good spot to make those because you'll need to have these memorized. What are the conditions? Well, the first one says that that function will be defined where x is c. So that is to say that f of c is defined. I plug in x equals c into my function and it gives me a y value. It's defined there. The second condition says that the limit as x approaches c of this function we're calling f would exist. Okay, the limit exists. Now we know there's a little bit more to that because in order for the limit to exist, recall that that means that the limit as x approaches c from the left has to equal the limit as x approaches c from the right. That's what it means for that limit to exist. So there's a little bit of checking to do with that second condition. And then our last condition says, well, we already know that the function is supposed to be defined, that the limit exists, but this last one states that our limit as x approaches c is actually going to equal the function value. So all these things are important, and this means that to be continuous, that we would have to check all three of these conditions. If for some reason one of whatever we're looking at or talking about fails one of these things, we would say that it's got a discontinuity or it's discontinuous. Okay, so I've drawn a graph in front of you, and we're wanting to know if this is continuous at x equals 3. Now, back in college algebra, you'd easily say, oh, no, I can tell. No, I had to lift up my pencil. It's not continuous. However, in this course, we're actually going to have to prove it. And so the suggestion is to go through each one of these conditions and check them. So I'm going to check the conditions, and I'm going to go with sequential order. And so the first condition to check is f of 3 defined? So I go over to my graph, I look where x is 3, there's an open circle, it's not defined. So I'm going to say no. So immediately, because it fails this condition, I'm going to say therefore it's not continuous at x equals 3. Okay, well that was simple. Not too bad. All right, here's our next one. We're going to call this one h of x, and I want to know, is h of x continuous where x is equal to 0? And again, I can look at this and I can tell you, no, it's not, but now I have to prove it. So going through our conditions, the first one says to check if h of 0 defined. So I've thought about this, I've written something, and sure enough, I look over at my graph and I say, yeah, when x is 0, I have a function value, and h of 0 is equivalent to -1. Perfect. Pass the first condition. It's going to fail somewhere, let's see. The second condition says, does the limit as x approaches 0 of our function exist? As I mentioned a few moments ago, or minutes ago, this actually means that I'm going to have to take the limit as x approaches 0 from the left and see if it equals the limit as x approaches 0 from the right. And if that is true, then we will say that the limit exists. And we will be able to say that it's past condition 2. Now looking at our graph though, we can see that as I approach 0 from the left, so I'm approaching x equals 0 from the left, I'm on this portion of the graph. I approach it from the left, and I would say that the limit as x approaches 0 from the left is -1. If I look at this other portion of the graph, approaching 0 from the right, here I am up here tracing along, I approach the y value of 1. So these indeed are not equal. Therefore, the limit as x approaches 0 of our function h of x does not exist. So we have failed the second condition, and I can now say that h of x is not continuous at x equals 0. Okay, let's get to another example here. We're going to see if this function g of x is continuous at the point where x is equal to 4. Now I provided you a graph, and again that you could probably look at it and just tell that this has to have your pencil picked up, so it's not continuous. So let's take a look at how we would show this for this course. The first condition I'm checking is, does g of 4 exist? I look at my graph. When x is 4, there is indeed a function value, g of 4 is equal to 1. Okay, first condition passed. The second condition says that I'm going to check to see if the limit as x approaches 4 of our function g exists. I'm going to check the left-hand limit. Looks like I'm having some issues here getting this thing to pick up my writing. But I'm going to check the left limit. And when I check the left-hand limit, I am tracing along this portion of the graph, coming from the left, x is approaching 4, and it looks like I get really close to the value of y equals -2. I will now approach 4 from the right. When I'm approaching x equals 4 from the right, I'm tracing along this graph, and again, it looks like I'm approaching the y value of -2. So it appears that my limit as x approaches 4 exists, and it's equal to -2. The third check, or the third condition that I have to do, is I need to see if the limit as x approaches this c value, which is 4, of our function, does it equal g of 4? Well, the limit as x approaches 4, we just found to be -2. We proved that that limit exists and it's equal to -2. Now, what was the value of g of 4? I can look at my graph, but I've also already done this in step 1 here. G of 4 is -1. Or excuse me, +1. Regardless, it doesn't equal. So because the statement is not true, it has failed this third condition, I can conclude that g is not continuous at x equals 4. Okay, the next thing I want to show you is just kind of a summary of continuity. These are the types of functions we'll be working with in this course. And so you can see we've got polynomial functions, rational functions, root functions, exponentials, and logs. So these are what we'll be working with all semester. When we're talking about continuity with polynomials, this is typically what we're most familiar with, working with polynomials. Where is it continuous? Well, for all x. And if you start relating this to the domain of your functions, this will begin to make sense. As we talk about rational functions, so we've got a numerator here and a denominator, your domain of a rational function depends mostly upon the denominator, unless we make the numerator more complex. But the denominator cannot equal 0. And so when you're talking about domain, you throw out all of those x values that would make the denominator evaluate to 0. And that would also be the same for where we would have a discontinuity. So where is it continuous? Our rational function is going to be continuous everywhere except for, in this case, if we're talking about polynomial over polynomial, where the denominator would evaluate to 0. So we again can relate this back to domain. Looking at root functions, when we talk about a domain of a root function, we want the radicand, or here ax plus b, to evaluate to be something greater than or equal to 0. So I don't want to take the square root of -9. That gives me an imaginary root, or plus or minus 3i. I want to be able to have something that is positive or equal to 0. So when we think about the domain and continuity, this again matches. We will also be talking about exponentials and logs and taking the derivative. Here are some simple examples of exponential functions and logarithmic functions, and an exponential will be continuous for all x's, so I can plug in, for example, our most basic 2 to the x. I could have 2 to the negative 100, get an answer. I could have 2 to the 0. I could have 2 to the positive 100. So our domain is all real numbers. We're going to be continuous everywhere. When you look at the logarithmic function, you cannot evaluate a log with a negative argument, or that is where the x is. So when you think about, and let's see if this lets me write on it. I'll go back to the other screen just in case. When you think about logs and the definition of a log and changing it to an exponential form, we should know that a log base 2 of 8 equals 3. That's because in exponential form, we have 2 to the third equals 8. Well, now, if I were to ask you to find the answer to maybe like log base 2 of -8, and you're supposed to respond to me what the answer is, you would go, okay, all I have to do is say 2 to some number is supposed to equal -8. Well, you can't actually do that because there's no way you can take this base 2, square it, cube it, raise it to any power that would give me back a negative number. So hopefully that makes sense as far as the domain with those logarithms. So I'm going to flip back quickly to that. Semi-quickly. And you can see, as I mentioned, that domain could not have negative numbers. It also couldn't have 0, since you couldn't have, like, for example, 2 to the 0 evaluate to anything other than 1, or 2 to any power evaluate to 0 itself. So here we are looking at the domain and how that relates to continuity. Okay, so what if I'm asked to find where the function is discontinuous? I would use those rules we just had a moment ago. And so one of the trickiest examples for students are those rational functions. And so perhaps our function f is defined as x squared plus 9x plus 89. And let's say our denominator is x squared plus, 9x. And let me think of a good example here. Okay, I actually switched that around. So if I asked where is this function discontinuous, I was given something that looks like this. I'm not able to cancel anything by factoring the numerator and the denominator, but I realize it's a rational function, and I am concerned about where the denominator is 0. And so what I would do is I would actually figure out where the denominator is equal to 0. And I would say at those x values, I would have discontinuities. And so let's see. So we're going to find two numbers that multiply to 20 but add to 9. And so we would have that x would equal -4 and x would equal -5. So we would have discontinuities at these x values. And it's as easy as that. Okay, let's look at our last type of example that we would run across. Perhaps you're asked to find the constant k that makes your function continuous. And it wants it continuous all over. And we are handed a piecewise defined function. We've got a curvy piece, and I say that because we've got a quadratic here in the top line. We've got this curvy piece for all portions of the graph where x is strictly less than 4. And then we've got this linear piece, it says, you can tell that by this second line here, for all portions of the graph where x is 4 or greater. So I've got these unknown k's here. I'm trying to figure out what that k value would be that would make this constant. So the first thing when you're looking at these piecewise defined functions to determine how you're going to define or make a k that's continuous, you start taking a peek at where I call the breaking points are. Well, where is this changing shape, where I called it like the curvy piece to the linear piece? Well, that point of interest where I think there probably could be a discontinuity is going to occur at where x is 4. So my point of interest, where I think there perhaps would be a discontinuity, is where x equals 4. And my job is to make sure that that is not going to be a point of discontinuity. And so I've got to come up with a way to make sure that this thing is continuous. Well, this goes back to thinking about the definition of continuity. Remember, there were three conditions that had to be true. It first said that the function would have to be defined at that point. So it would have to be defined where x is 4, so that means g of 4 would exist. It also said that the limit exists, so that means the left-hand limit would equal the right-hand limit. And then that final condition said that that limit that we just said would exist must equal that function value. So I can kind of summarize all this stuff up. What I need to be able to establish is that the limit as x approaches 4 from the left of my function needs to equal the limit as x approaches 4 from the right, because this is saying my limit would exist. That satisfies condition 2. But condition 3 says, well, this limit would have to be the same thing as the function value, which is g of 4, which must exist by condition 1. So I mean, think about that. You might want to pause it and realize that me just writing this statement, these equal, that's what I need. This is going to establish that I've met all the criteria so that this function g would be continuous. Well, how am I going to do that? Well, I'm going to say I'm going to look at the left side of this function as I approach 4, the right side as I approach 4, and then I want to make sure that it's equivalent to whatever I would get when I evaluate or when I let x be 4. So I'm going to do all these things at once, and you probably will have to go back through and read over it again. So let's take a look at what it would be like if I approach 4 from the left. So I look back at my piecewise defined function, and if I'm approaching 4 from the left, that means I'm starting at something less than 4. Well, my graph is defined where x is less than 4 on this first piece. And so I'm going to know that I'm going to use that part of the function to find my limit as x approaches 4 from the left. But at the same time, I need it to evaluate when I substitute in x to be 4. So I'm taking this part of the function. I'm going to evaluate it when x is 4. I don't know what my k is, that's what I'm looking for. And I'm stating that it has to equal whatever my function value would be using the appropriate part when x is, or when I approach rather g from the right. And so that means I'm looking at this second chunk here. And so I'm looking at the limit from the right. That would mean I work with kx plus 20, but again, I need to evaluate and make it equivalent to whatever it would be when I let x be 4. So I would plug in x to be 4, and that would say k4, but we know we don't write it like that, so I'm going to put 4k plus 20. So what I'm trying to do is establish it so that my limit exists. That means these two things are equal, and that means that it equals, that limit equals, then the function value, which means I'm going to plug in x before. So I actually have taken what seemed to be something pretty complex and I've made it into solving a quadratic. And so we go through this process of solving this quadratic. So I'm just going to do a little bit of simplifying here. And I go, okay, if I'm going to solve a quadratic, let's put it in standard form, and I can factor, I can use quadratic formula. So I'm going to put it in standard form, move everything from the left to the right in this case. So if I'm going to move everything from the left to the right, I now have a positive k squared. Right in descending order, so I have a plus 4k, and I've got to subtract over the 16, so I should have a plus 4. Now I'm solving for k, and that's what this problem tells me to do. Find the k so that this thing is continuous everywhere. Can I factor this? Do I need quadratic formula? Well, I'm going to check. Factoring would be the easiest. I set up my two sets of parentheses, and I should have k plus 2 times k plus 2. That's correct. And so I would solve, and I would get k to be negative 2. So I would need k to be negative equal to negative 2. So that means back up here, it didn't tell me to do this portion, but just to go a little bit further, this means that this would look like x squared minus negative 2 squared, right? And this would be negative 2x plus 20. So all I had to provide, though, was that k value that made this continuous. You would also do this similar thing if we had multiple conditions. Perhaps there's some more conditions that say, like, we're looking at where it changes where x is equal to like negative 1 or 0, and those would be points of interest where you do this similarly. And that should wrap up continuity. Make sure that you understand all those conditions to ensure that something is continuous.